Okay, Chapter 3 is about numerically summarizing data. So in Chapter 2, we dealt with summarizing data through tables and graphs. And in this chapter, we're going to learn what it means to summarize the data numerically. So in 3.1, we're going to be talking about measures of central tendency. And you can expect in this section to learn what the arithmetic mean is, a median, what it means for a statistic to be resistant, and the mode. Just as a recap, we have already talked about this, but a parameter is a numerical study about a population, and a statistic is a numerical study about a sample. So there are a couple terms that you need to be familiar with. We've got arithmetic mean, and it basically is found by adding up all the values in your data set and dividing by the number of observations. There are two types that we talk about: population mean, which is denoted by this symbol, mu. My mu looks like that. So if you see that, that's what it means. And you talk about that when it represents the mean of a population. Then we've got sample mean, which is represented with X bar. Mine looks pretty similar to that. And that is when you have the mean of the sample data. This is how you will find those means. You will be given this formula on your formula sheet. And just a couple things. They're pretty much the same, except mu is used to denote population, and X bar is used to denote sample. And in population, you use capital N because that represents population size. And in sample, you use lowercase n because that represents sample size. This says the following data represent the travel times in minutes to work for all 7 employees of a startup web development company. And there's the data. And it says compute the population mean of the following. So first off, why is this a population mean? Because it's talking about all 7 employees. Anytime the word all is used, then we know it's talking about everybody. So I'm going to go ahead and add these up. Not 8, 7. And I'm going to add these on my calculator. So 23 plus 36 plus 23 plus 18 plus 5 plus 26 plus 43. I get 174 divided by 7. And when you do that, you will get 24.8571. And so that's how we do that. And then B you can do by randomly selecting 3 and trying that on your own. I'll do 1. You can do 1 as well. I'm going to do it over here because I'm running out of room. So that was A, this is B. Let's say I put all the numbers in a hat and randomly select 23, 23, and 43. I can use 23 twice if I randomly selected it because there are 2 commute times that represent 23. When you add all those up, you'll get 89 divided by 3. I get 0.6667. I'm going to do this up here. B is equal to 29.6667 that would be an X bar because it is a sample mean. You also have a median, which sounds like medium. And when I think of a medium shirt size, I think of middle. And that variable is the value that lies exactly in the middle of the data. And so you need to arrange it in ascending order, which means smallest to largest. And we use capital M. So I try to make it as easy as possible because mu is also an M. So it's easy to get those two confused. Do know that wherever M is, that median, 50% of the data is at or below that value, and 50% of the data is at or above that value. I apologize, this slide did not download for some reason. I will read the steps to you and I'll explain it on the next slide as well. Step 1 is arrange it in ascending order, so from smallest to largest. And then step 2 is determine the sample size. And then step 3 basically says if our sample size is odd, then we'll have one perfect value in the middle, exactly one middle value. And if it's even, then we'll have two values and we just have to average them together. This says compute the median of a data set with an odd number of observations, so kind of like what I was telling you about. So here's the steps. You want to put it in ascending order first. So 5, 18, 23, 23, 26, 36, 43. And as you do that, if you want to mark out, what you've used, that's not a bad strategy either. And then you can say, I know I've got 7 observations, aka 7 employees, so I know the middle number is going to be 4. Or what a lot of people do is they take some from each side till they get to the middle. So 1, 1, 2, 2, 3, 3. Okay, that's my middle number. So my median is 23. Let's say I added an employee, so 70. So I'm going to do the same thing, and I want to find the median. It's pretty much going to be in the same order, except we're going to add 70 at the end because that's the largest value. So if I do kind of that same process, I now have 2 numbers in the middle. When you have 2 numbers in the middle, you average them together. And it needs to make sense, right? 24.5 does lie right there. And that represents the middle number. If you forgot to divide by 2, you'd get 49, which is somewhere over here, and that wouldn't really make sense that it would be the middle number. So what does this tell us? And for the other data as well, this number, all the values to the left of it represents the lower 50%, and all the values to the right of it represent the upper 50% of your data. Okay, so let's say we fire the 70-minute commute person and we hire another person, 130-minute commute. Well, first off, before we hired him and we got all that data earlier, just with the original data set, this was our information. Let's say we hire someone with a 130-minute commute. Now what is the mean and median? So, excuse me, if I add that 130-minute commute in there and divide now by 8, my mu is going to be 38.375. It made that average go way up, right, from 24 to 38. But my median, if I put that 130, it's going to do the same thing that it did with the 70. It's just going to add another value, And then we're going to have to average those middle values together. So we'll pretty much get the same thing, 24.5. So as you can see, median didn't move as much, right? It just moved a little bit. It changed a little bit because it had to average those middle numbers together. But mean changed a lot because it made the average go way up. This is called a resistant measure. So a numerical summary of data is said to be resistant if extreme values, whether that be large or small, do not affect its value. The median is resistant, right? It did not move very much. I'm going to say not much change. To that extreme value that we saw versus median, and it changed a lot. It went up because the extreme value was very large. So depending on the relationship between your median and your mean, they could produce different shapes. And we could compare the mean and median and be able to tell what shape it is without having to draw a histogram or, a dot plot or stem and leaf or anything like that. So that's kind of cool. But it's said to be skewed left if the mean is smaller than the median, and you kind of have a picture right here. If they are relatively equal, 24 maybe is my mean and 25 is my median, that's pretty close. They would produce a symmetric bell curve. And then if the mean is greater than the median, then it's going to produce something that looks skewed right. You are given this on your formula sheet. You're not given the pictures, but you're given this to compare them, and you can base what shape it is on that information. Okay, so example 5 says to describe the shape. So we're actually, I'm not sure why some of my information down there is not working, but I'm going to do this on the next page. I'll show you what the median is for this page, and then I'll do the mean on the next because I've got a little more space. So if you look, it's already in ascending order, and it's going like this. All those, and it's starting back. All those, starting back. All those, starting back. All those. So this is the largest, and this is the smallest. And we want the middle number. So it's definitely not going to be any of these columns because those are the outer numbers. So then I can kind of start going, okay, 1, 2, 3, 1, 2, 3, all the way to the middle number. 1, 2, 3, 1, 2, 3, 1, 1. These are my two middle numbers. So remember, if I'm going to, if I've got two middle numbers, I've got to average these two together. By doing that, I'm going to add them together and divide by 2. And I'm going to show you what I get on the next page. So if I added those two together and divided by 2 for my median, I would get 148,700. Okay, I'm just going to tell you that I would have given you the summation, aka what all these added to, because that would be a lot of numbers to add together. So I'm going to eventually erase this part, but let's say all of the houses added together to be this 5 million number. And let's see, I believe there were 32 of them. 2, 4, 6, 8 times 4, yes. There are 32. So I'm going to divide those together. Divide those by each other, I'm sorry. So for my mu, I would actually end up getting 168,320. And I'm going to write my median again. which was at 148, 700. So if you're going to compare these, mean to median, what is the relationship? My mean is greater than my median. Whenever this happens, we have a skewed right. And I could determine the shape without even having to draw this histogram. This is all about to go away. But if I made the histogram, I could verify my results, and it is skewed right. Do that again. The last measure of central tendency that we're going to talk about is mode. It's the most frequent observation of the variable that occurs in a data set. We can have three things happen: no mode, one mode, or more than one mode. If no observation occurs more than once, we say there's no mode. Mode can be used for qualitative or quantitative data. And mode does not have a symbol. We just say mode is this. We just spell it out. So this table represents the state of birth for our vice presidents, and we want to find the mode. So this frequency table is our friend if we're trying to find mode. We are looking for the number that is occurring the most, which is 8. And there's no other 8. If there was another 8, we might have 2 modes, but in this case, we only have 1. Okay, so we're going to find the mean, median, and mode of all of these data. So you can kind of verify. I'm just going to go through and tell you what it is. And I suggest finding this on your own and then making sure you've got it with my answers. You can feel free to pause the video. So my mode on A is 6 and 10. My mode on B, I don't have any numbers. Well, hang on, let's go back to A. Because 6 and 10 happened the same frequency. They both happened twice. I have 2. On B, because I have no numbers that repeat, I have no mode. And on C, I've got a lot of numbers that repeat themselves, but the only one that repeats itself the most is 16. Next, I'm going to do my mu. Add them all up. Divide by however many there are. On A, you should get 9. B, you should get 24.8333. I'm only going to go to one decimal place because I'm afraid I'm going to run out of room. And on C, you get 15.5385. Once again, I'm just going to go to one decimal place. Let's see if I'm going to find the median of this data. I'm going to end up getting 2. 8 and 9, average them. 8 and 10, average them, you get 9. Here I get 25 because I had to average 23 and 27 together. And here I get 16. Now, it's not asked of you, but if you were to comment on the shape of all these are the same, so this one's going to be bell-shaped. These are not the exact same, but they're very close, and if that happens, bell-shaped, and the same thing with these. They are all bell-shaped or symmetric. This is just a summary of everything that we just learned. If you want to print this off to have as a little summary sheet, go for it. But again, it's just the measures of central tendencies, mean, median, and mode, and how to find each one of those. Okay, 3.2 talks about measures of dispersion. In 3.2, we're going to talk about the range, standard deviation, variance of a variable from raw data. We're going to talk about something called the empirical rule and Chebyshev's inequality. So it says, to order food at a McDonald's restaurant, one must choose from multiple lines. and at a Wendy's restaurant, one enters a single line. The following data represent the wait time in minutes for a simple random sample of 30 customers at each restaurant during the lunch hour. For each sample, answer the following: what was the mean time, and draw a histogram of each restaurant's wait time. I've gone ahead and found the mean for you just to save time. If you want to verify, you can, but this is a lot of numbers. I added them all up and divided by 30, and I actually got 1.39 for both restaurants. So I can expect to be waiting 1 minute and 39 seconds at each one. Does that mean that regardless of if I go to Wendy's or McDonald's, I'll definitely always wait the same time, or not? Is there a little something more to this? And that's what we're going to be thinking about. Here are the histograms for the wait times. They look kind of similar, but a lot of McDonald's is here. So it looks like McDonald's gets a lot of theirs in and out, but we've still got some people that have to wait up to 5 minutes. And it's pretty spread out, McDonald's is. I mean, it's all through here. Wendy's, the bulk of theirs is here, so maybe I know that I can for sure get in and out within half a minute to 2 minutes. And there's one a person who waited maybe up to 4 minutes here if you got unlucky, but that's not as bad as 5 minutes like McDonald's. So maybe we can go a little more into that and explain what it means. What I just kind of talked about, that 4 minute wait and 5 minute wait, that's what we're going to learn a little bit more about today, and that's called dispersion, and it's the degree to which the data are spread out. We can learn many ways to measure dispersion. There's 3 ways that we're going to talk about in this section: range, standard deviation, and variance. Out of those 3, range may be one that you've heard, if any. Range we represent with R, and you can find it by finding the largest value and subtracting it from the smallest value in a data set, or you can also think of it as the max minus the min. This says the following data represents travel times in minutes to work of all 7 employees of a startup web development. Find the range. That's my min value. And 43 is my max. Once you get those 2 numbers, you ignore all other numbers. You only care about the min and the max. And so if I subtract them, my range is 38 minutes. That's the range, right? From the smallest value to the largest value, how many minutes there is between them. A standard deviation is how far on average each observation is away from its mean. That's very important. The population standard deviation of a variable is symbolically represented by sigma. I do my sigma like this. So population standard deviation is represented with sigma. Once again, we've got different symbols for population and sample as far as standard deviation goes. The sample standard deviation is represented with an S. So the population standard deviation formula looks kind of scary. Once again, you're given this on your formula sheet. And there are 2 ways to compute population standard deviation. This is one of them, and this is the way that I am not going to teach you. Do know that this exists, but I'm going to teach you with the formula that you see on the next slide. This is another way, and this is the way that I'm going to teach you. It looks similar, although it's a little different, and I think from someone learning it from a distance that this would be a little easier to figure out how to do. So, with that formula in mind, I would write it down, although, like I said, you're given it on your formula sheet. Well, let's talk about it really fast. It's the square root of the sum of x squareds So that minus the sum of x, square that number, divided by big N, which is your population size, all divided by N. So you got to be careful about that. And we're going to kind of take it step by step and go from there. This says the following data represents travel times in minutes to work for all 7 employees. Compute the population standard deviation for these data. We are just using the computational formula. So, basically, you're going to have 2 columns. One with x and one with x squared. All these numbers, these commute times, that's your x. So I may not be able to fit it on this line, and if so, I'll have to keep going over here. But 23, 36, 23, 18, 5. Yeah, I definitely can't fit it on there. 5, 26, 43. X squared is exactly what it sounds like. You're going to square these values. And remember, square means to multiply it by itself, not times 2. So 23 squared is like 23 times 23. 529. And I'm going to do that for each one of them. So 1296. 529. I already had that one. 324. 25. 676. And 1849. And part of the formula, and I'll write it down. Well, I'll write it down up here actually. I'll wait. Part of the formula says to add these all up. So the summation. So I'm going to add 23 plus 36 plus 23 plus 18 plus 5 plus 26 plus 43. And I'm going to get 174. X squared, we're going to add next. All right, so 529, 1,926, right? Add them all together. If I add them all together, I'll get 5,226. Write that down if you don't have it, because I'm about to erase this so I have more room. Okay, so really quick, I'm going to write this formula down. Best of my ability. It is, sum of x squared minus sum of x's squared divided by n, all divided by n. And that's the one from the last slide, if you can't read that very well. We just said when we added up all those x's, which is called the sum of x, we got 174. That little e-looking thing means summation. Then we squared them and added all those together, which is the sum of x squared, and we got 5,226. This is what I did right before I erased it. Okay, so if I were you, I would do these little steps at a time. So this is going to look like this. This 5,000 number goes here. 5,226 minus. This 174 number goes here. $174 squared divided by n, however many people you're talking about. I almost put n, which is 7 in our case, all divided by 7. If you try to do this all at once in your calculator, it's going to probably not give you the right answer. It requires a lot of parentheses. So I would do this part first, and then just do it one little slice at a time. If you do that part in your calculator, you should get 4,000 325.1429, all divided by 7. So the next thing I would do is subtract these. When you subtract them, you will get 902.8571 divided by 7. It's all square rooted. So then I would go ahead and divide them. Whoops. When I do that, I get 128 point, I believe that's 479746. So this part's important. A lot of people do all this and then they say that's the standard deviation. That's actually something, this number, this 128, this is actually called the variance. It's the number you get right before you square root it. So I'm going to go ahead and square root it to get my standard deviation, my sigma, which is 11.3569. I know it's a lot of work, but hopefully with some practice you'll feel okay about it. So we've been talking about population standard deviation. Now we're going to talk about sample standard deviation. Once again, there is another formula that you can use if you want. I'm not going to use this formula. I'm going to use the one on the next slide, but they're both given to you on your formula sheet. So this is the one I'm going to use. It looks very similar to what we just did, except S equals, because it's sample standard deviation. And instead of big N, you're using little n divided by little n minus 1. The reason we are doing little n minus 1, first off, it's called a degrees of freedom. And you'll learn more about that later on. But the first n minus 1 observations have freedom to do whatever they want. But the nth value has no freedom. It must be whatever value forces the sum of the deviations about the mean to equal 0. So let's do this again. And let's say we take a sample of 3 people from our startup company. So those are our values. And we want to find the sample standard deviation. And so we're going to go about this very similarly. We're going to create an x squared. Actually, I'm going to do that a little higher. So maybe I can fit all my data. So I've got 5, 26, and 36. So 25, squaring them now, 676, and 1,296. And again, I'm going to add them together. I'm going to add these together. 5 plus 26 plus 36, I get 67. Add the x squareds together, 25, 676, 1,296. I get 1,997, sorry. Okay, remember those numbers. I'm about to erase this. So the sum of my x's is 67. The sum of my x squared is that 1997. Here's the formula. Sum of x squared minus sum of x's squared divided by n, all divided by n minus 1. Okay. So I'm going to plug this in. Again, that 1997 is that first number. Oof. That 67 is that sum of x number. We're talking about 3 employees and then all divided by 3 minus 1. So once again, I would tackle this part first, clean it up, and then go from there. 1997 minus, when I did 67 squared divided by 3, I got 1,496.333. All divided by 3 minus 1 is 2. Same thing, I would then tackle this. I would subtract them from each other. When I subtract them, I get 500.6667 divided by 2. I did not need that much of a square root. Sorry about that. Divide that by 2, right? We're doing the square root very last. I get 250.33333. Okay, remember, this number, we haven't talked about it very much. That's your variance. That's what happens right before you square root it. A lot of people forget to square root it. Don't forget to square root it. When I square root it, I get 15.8219. I'm going to put S equals. And that's your sample standard deviation. All right, so I'm just going to give you this information because this would be a lot if I asked you to do this. So the wait time, let's see, I need to find it now. Okay, the wait time at Wendy's, if I were to do the standard deviation, is 0.7384. And then at McDonald's is 1.2649. Sorry. And I did that by basically doing that for all of these numbers, so that would take forever, right? Basically, the smaller your standard deviation is, because Wendy's has a smaller standard deviation size, we can rely more on them. We can say, I know, okay, let's see, what was my X bar? It was 1.39, I believe, for both of them. Sorry if I got that wrong from the beginning. We can say because Wendy's standard deviation is smaller, it's going to be closer to the mean a lot of the time. I know I can go in and out in about 1:39 more times than McDonald's because their standard deviation is larger. Well, maybe sometimes I'll get lucky and I'll get in and out in maybe 30 seconds. But maybe sometimes on the opposite side of that spectrum, I'll have to wait a little longer. And so that's kind of an introductory of what standard deviation can tell us. Okay, the variance of a variable is the square of the standard deviation. So population variance is sigma squared, right? It's what happens right before you square root it. So if you wanted to get back to it, you'd square it. And the sample standard deviation is S squared. And so for the examples that we did, when we were trying to find sigma, that 128.9796, it's that number right before you square root it. Because what was our sigma here? Let's see. It was 11.3569. If I were to get that number and then square it again, I would get that number. So it works either way. And then for sample, when we were doing this, we got 250.333. That number is our variance right before you square root it, so it works either way. Okay. I'm actually probably not going to do this because this is actually what I just talked about. This is when we added up all those numbers and we got to the very end and we got, there we go, 128.9796. So that variance is that 128.9796. And then that standard deviation is the number that happens when you square root it and go from there. So that population variance is always right before you square root it. And this is the example that we did earlier with when we wanted to find standard deviation. So this is talking about the empirical rule. This is a rule that you can use when the distribution is roughly bell-shaped. I'm going to explain a little bit more of this on the next slide with a picture, but it says approximately 68% of the data is within 1 standard deviation of the mean. 95% of the data is within 2 standard deviations of the mean. And 99.7% is within 3 standard deviations of the mean. Here's a picture that represents that. So my mean's going to be in the middle. And then it says if I go within 1 standard deviation of the mean, that represents 68% of my data, which kind of makes sense because that's where the bulk of your data is. If you wanted to find how much is on each side, then you'd do 68 divided by 2 and you'd get 34 and 34. If you go within 2 standard deviations of the mean, 95% of your data lies within 2 standard deviations of the mean. Well, how do I get these 13.5 numbers? Well, we've already used 68, so 95 minus 68 would give us 27, and there's 2 of them, so 13.5. You get the same for the 99.7. That amount of data lies within 3 standard deviations of the mean. Subtract that from 95, divide by 2. That's what each of those is. Well, how do I find that data that lies outside of the 99.7? Well, there's 100% total, so 100 minus 99.7 is 0.3. Divide by 2, you get that 0.15. This may not make any sense right now. I hope that it makes a little more sense with a picture, with actual data that we'll see in a second. Okay, so this says the following data represents the serum HDL cholesterol of 54 female patients. Here's all your data. Compute the population mean and standard deviation, which I have on the next slide, and a histogram on the next slide. These are what we care about. The percentage of all patients that have serum HDL within 3 standard deviations of the mean according to the empirical rule. Well, remember that rule that we just looked at? Anything that's within 3 standard deviations of the mean is 99.7% of your data. Always, 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 no matter what you're looking at when you're using the empirical rule. Then it says determine the percentage of all patients that have serum HDL between 34 and 69.1. So that's actually using this data that we'll compute in a second. And then determine the actual percentage. So we're going to use the empirical rule, and then we're going to look at the actual percentage, which I'm going to do on this slide. So I'm going to kind of go out of order. But if I want to know the actual percentage of patients between that have this serum between 34 and 69.1, I'm going to go through and count all of them. So 41's between 34 and 69. That is 2, right? So on, so on, so on, so on. 75's not, so I'm not going to circle that one, right? And I just keep going through these and circling all the ones that are between 34 and 69.1. And I would end up having 45 out of, it told us, 54 patients, which is 0.833. or as a percentage, because it said the actual percentage is 83.3%. Okay, so I'm going to remember that 83.3. And when I do this one on the next slide, I'm going to see if I can get close to that by using the empirical rule. Okay, so remember how it said we've got the mean and standard deviation. That's just given to you. You didn't have to compute that because that was a lot of data to have to work with. And then with this bell shape, I can say at least that it's roughly bell shaped, so I can use the empirical rule. So here's what the empirical rule says, and you can go back to that picture if you want. I'm going to draw a little line. The mean always goes in the middle, so, and I'm going to write this kind of sideways so I don't run out of room. The mean was 57.4. And then as you go to the right, you're going to add standard deviations to get that next value. So my standard deviation is 11.8. So I'm going to add 11.8 to 57.4, which is 69.2. And then I'm going to do it again. 81, 92.8. So basically, for each of these, I added my standard deviation. If I want to go backwards, I'm going to subtract 11.8 from the mean. So I'm going to go ahead and put the values that I would get. 45.6, 33.8, and 22. So I just keep subtracting 11.8 from the previous number. Keep on subtracting to get those values. The question we were asked was, what percent of all patients have a serum level between 34, so 34 is about right here, and 69.1, so that's about right here. Okay, now let's think back. So here's my mean to all those percentages that we were given on the empirical rule. Remember, this is 34 and 34, or within one standard deviation of the mean, it's 68. And then remember that little percentage was 13.5. So if I add them all up, I get 81.5%. So it told us the percent of patients that lie within X amount of standard deviations of the mean. And remember when we actually did it, we got 83. So it's actually really close to the actual number. And so what we just learned is we can use the empirical rule to estimate the amount of percentage that maybe these patients lie within a certain standard deviation or whatever it is that we're talking about. So the empirical rule is a very good estimator. Last thing we're going to talk about in this section is Chebyshev's inequality. The thing about Chebyshev's is it does not have to be bell-shaped. Not required. Versus with the empirical rule, you do have to have a bell shape. So it says for any data set or distribution, at least 1 minus 1 over k squared times 100% of the observations lie within k. Standard deviations of the mean, where k is any number greater than 1, that is at least 1 minus 1 over k squared, 100% of the data, between mu minus k times sigma and mu plus k times sigma, and k needs to be greater than 1. So let's do it. It says use the data from the previous example, use Chebyshev's theorem to determine the percent of patients who have serum level HDL within 3 standard deviations of the mean. So that 3 is your K. So 1 minus 1 over K squared times 100. So in this case, 1 minus 1 over 3 squared times 100. If you do that in your calculator, you're going to get 88.9%. So I'm putting my percent up there. And then it says determine the actual percentage of patients who have serum HDL between 34 and 80. So this is the one where we go back to the data and we circle and we count however many out of 54 total patients. And 52 out of those 54 patients had a serum level between 34 and 80.8. I get 0.963, and as a percent, that's 96.3%. So it's pretty close to the actual number of to the actual percentage. Okay, so we're going to section 3.4. We actually don't do 3.3, and in 3.4 it says to measure position and outliers. And in this section, we're going to be talking about z-scores and percentiles, what it means to interpret quartiles, interquartile range, and find outliers. So we're going to be talking about this question. We're going to ask it first so you can kind of be thinking about it. The mean height of males 20 years or older is 69.1 inches with a standard deviation of 2.8. The mean height of females 20 years or older is 63.7 inches with a standard deviation of 2.7 inches. Data is based on information obtained from the National Health and Examination Survey. Who's relatively taller? Relatively is what we're going to be looking into because we know that, Kevin is taller than Candace, right? 83 versus 76. But who's relatively taller? Basically male versus female, right? Who's relatively taller for a male or a female? And once again, my slide is doing some weird stuff, but thankfully I have it on the next slide, so I'm just going to keep going. Okay, so when we see that word relatively, we can start comparing things using a z-score. We can compare apples to oranges now, if we put them on the same scale, basically. And so a z-score is a value that results from inputting a data value in the z formula for whatever x value you're looking at. The z-score represents the distance that a data is from the mean in terms of standard deviations. There is a population and a sample z-score, right? Like everything else. Really the only difference is with population we're using mu and sigma, and with sample we're using x bar and s. You go about finding the z the same way. And a z-score is unitless. And when we talk about z-scores, the mean is 0 and standard deviation is 1. Here's some things you need to know. Again, z-scores don't have units. Most of the time, z-scores will be between -3 and 3. That is because of the empirical rule. Remember, between -3 and 3 standard deviations represent 99.7% of your data. So if something lies outside, they're either really small or big for whatever you're looking at. Values that are larger than the mean will have a positive z-score, and smaller than the mean will have a negative z-score. And again, z-scores just give us the ability to compare things that we wouldn't normally be able to compare. So let's go back to that example. And we want to know who's relatively taller. We can do that now with z-scores. So because it is using information based on this national survey, we can say that we're going to be using population mean and population standard deviation. So I'm going to do them both, one for Kevin and one for Candace, and I'm not going to have enough room to do all of this, so I'll have to erase as I go, but z is equal to x minus mu divided by sigma. Okay, let's do Kevin first. So for Kevin, let's find information. It says the mean height of males. I'm going to assume Kevin's a male. Is 67. with a standard deviation of 2.8. So our mu for Kevin is 69.1, and the standard deviation is 2.8. So we've got mu and sigma, but what is that x? That x is what you're trying to get information or compare it to the mean and standard deviation. So we're looking at Kevin's height specifically, so that's going to be our x. Your x can change. It's whatever you're looking at. Whenever you put this in your calculator, make sure to subtract these first and then divide, or you're not going to get the right answer. So when we do this, we get 4.96. That's a very, very, very big standard deviation. 83 inches is really tall, though, so he's probably 7 foot something, which is pretty unusual, so that's why the z-score is so big. If you want to see, if you're a male and you want to see where you stand, put your information in and see if you've got a small z-score, big z-score, based on average, right? If you're 69 inches tall, your z-score is going to be really small because it's really close to the mean. Okay, I'm about to erase all this. So Garrett is 4.96. Let's see what Candace is. So Candace is a girl, so we've got new information. All right, mean height of females is 63 with a standard deviation of 2.7. And we're looking at Candace specifically, and she's 76 inches tall, which is still really tall for a female. I think that's, 6'4", so she's probably going to have a big z-score as well. So 76 minus 63.7 divided by 2.7. Once again, subtract these first. And I get 4.56 for her. So Kevin was 4.96 and Candace was 4.56. And so they're really both extreme z-scores because most of the time, like we said earlier, it's between -3 and 3. But we can say that Kevin's relatively taller because we've put them on the same scale now and he's still got a bigger number. Let's do another example, and I suggest that you pause and try it on your own. So according to a 2006 article published by the National Institute of Health, the mean gestation period of humans is 272 days with a standard deviation of 9. Suppose a birth is selected at random whose gestation is 306 days. Is this unusually long? So what I'm actually looking at is 306. So remember, it's x minus mu divided by standard deviation. You are given this formula, so you don't have to memorize it, although you probably will by the time it's all said and done. And when I simplify it, I get 3.78. Is this unusually long? Yes. Pretty much anything outside of -3 and 3 is very unusual. It's just, and in this case, it's unusually long because we get a positive z-score. Okay, next thing we're going to talk about is percentiles, which is denoted P sub k of a set of data, and it's a value that is in the k percent of observations that are less than or equal to that value. So basically, whenever you talk about percentiles, for example, a lot of people talk about percentiles when their baby's born. And so here's 25th percentile. Let's say my brother was in the 25th percentile for weight whenever he was born. So that number means you're bigger or better than that amount of people. So if he's in the 25th percentile, then for weight, then that means he weighed more than 25% of Americans. Let's see, if I'm in the 60th percentile for height, that means I'm taller than 60% of people or women or whatever it is that percentile is based off of. So let's do an example. The GRE is a test required for admissions to many grad schools. The University of Pittsburgh grad school requires a GRE of no less than the 70th percentile for admissions. And so what this means is, if you're in the 70th percentile, then that means you did better than 70% of people who took the test. But on the flip side, it means you're in the top 30%. So kind of see the difference between those. You know, in high school, you would say maybe I'm in the top 10%. If that's the case, then you're in the 90th percentile because you did better academically than 90% of students. Going more specifically into percentiles, we have quartiles, which sounds like quarters, which deals with force, right? So the first quartile breaks the data into 25%. Q1 to Q2 to the second quartile is 25%. Q2 is also called the median. And from Q2, you've got the lower 50% of the data because 25 plus 25. And you've also got the upper 50% from the median, right? Q2 to Q3, quartile 2 to quartile 3 is 25% of the data. And then Q3 to the max value is 25%. So another way for smallest is min and largest value is max. So you can pretty easily see maybe that Q3 represents the 75th percentile because it represents the top, that 70% of the data is behind it, 25% is above it. However you want to think of that, but that is a visual of what that looks like. So here's how we find quartiles. We need to arrange the data in ascending order. It's very similar to mean. Then find the mean. And then once you find the mean, you can find Q1 and Q2 by basically finding the mean of the lower half and the mean of the upper half. And you can do a couple different things if it is an odd data set or an even data set. So we'll kind of see what that looks like. Okay, it says we've got these group of students that collected the speed of vehicles traveling through a construction zone, and the speed posted was 25 miles an hour. Here's what cars were actually going, 14 randomly selected cars, and they were so nice, and they already put it in ascending order. So we've got 14 vehicles, which means we're going to have two middle numbers. And those two middle numbers are actually going to be 32 and 33. So to find my Q2, aka my median, I'm going to average them together. And I'm going to actually end up getting 32.5 for my Q2. So that's where my Q2 is. Now to find my Q1, I'm literally going to take this and look at all the numbers to the left of that black line and find the middle number. So 1, 1, 2, 2, 3, 3. We've got one middle number of the lower half basically, right? And so that represents my Q1. So my Q1, oops, I need to put a 1, is 28. We're going to do the same thing for Q3. 1, 1, 2, 2, 3, 3. And I get a perfect number in the middle. The middle of the upper half, I should say. Sorry. So my Q3 is 38. You could also say that your minimum was 20 and your max is 40. So there's a lot of things that you can take from this. Also, once you have your Q1 and Q3, you can say, at 28, that 25, the lower 25% of the data lies here at 28 and below. And at 38, the top 25% of the data lies here. Above at 38 or above, or the lower 75% lies at 38 or below, right? You can say a lot of things once you find your quartiles. So that was with an even set. Let's see what happens if I have an odd set. So if I were to find the median of these numbers, the perfect middle number, it's going to be 83. That's going to be my median, aka my Q2. Once you get that perfect middle number, right? Earlier, we were able to just split it in half because there are two numbers. Once you have that median, you basically ignore it. Ignore that number and now find the middle number of the lower half. So that's when we go through, right? 1, 1, 2, 2, so on, so on, so on, until we find that Q1, which is actually going to be 71. Same thing with the upper half. 1, 1, 2, 2, so on, so on, so on, until we find that Q3, which is 90. We've got something called an interquartile range, which is the range of the middle 50% of the data. To find the IQR, you do Q3 minus Q1, and that gives you that middle 50. It shows the spread of the middle 50%. And we will use IQR to find outliers, which we'll talk about very soon. Okay, so I'm gonna go back. Remember, our Q1 from the speed data was 28, and our Q3 here was 38. And then for grades, this was 71 and 90. So it wants us to find the interquartile range, aka IQR, which is given to you on your formula sheet. And it is Q3 minus Q1. So our IQR here is 10. This one, 90 minus 71. Our IQR here is 19. Okay, so if you want to talk about resistance measure again, suppose we had a 15th car travel through the construction zone at 100 miles per hour, very fast. How does this impact the mean, median, standard deviation, and interquartile range? So here's without it, all the data that we computed, and here's with. So let's see, the mean changed, right, from 32 to 36. Standard deviation changed a lot, but it looks like median and IQR stayed resistant. So we can say that these were the most resistant measures. We already knew that median was resistant, but now we know that IQR is also resistant. Okay, so we're going to talk about outliers now, and outliers are extreme observations. So that 100 mile per hour car that we just talked about, that would probably be an outlier. It could be extremely small or extremely large. That's making our data do something and maybe making it look more extreme than it actually is. Here's how we find outliers. We need Q1 and Q3. Then we need to find the interquartile range. And then there's a little formula to finding quartiles called fences. The lower fence, and again, you're given these on your formula sheet, is Q1 minus 1.5 times IQR. And upper fence is Q3 plus 1.5 times IQR. So we basically create these fences on our data, and if any of our data lies outside these fences, they're called outliers. And so that's what we're going to be looking for. Okay, it says determine any outliers for the data that we were given. So it's going to be kind of hard to do this without the data right here if I've already done it. So if you want to go back and take a picture of that data, that's fine. Go ahead and do that. And if not, you can just stay with me. So speed data. I'm just going to, actually, here's Q1 was 28. Q3 was 38. And then our IQR was 10. Okay, so, and I'm going to write those lower and upper fences up here. It's Q1 minus 1.5 times IQR. Q3 plus 1.5 times IQR. Okay, so for speed data, it's 28 minus 1.5 times IQR, which is 10. I get 13. And then 38 plus 1.5 times 10, I got 53. So you're looking to see if any values lie outside of these numbers, 13 and 53. Basically, did I have anyone go slower than 13 miles an hour or faster than 53? In that original data set, there were no values that were outside of these fences. So in this case, we have no outliers. Now, if you were to add that person who went 100 miles an hour, yes, you would have an outlier. Okay, grade data. So Q1 was 71. Q3 was 90. IQR is 19. If we do this again, plug in this formula for my lower fence, you will get 42.5. For my upper fence, you will get 118.5. Well, we know there's not going to be anyone that lies out of 118 because the grades only went up to 100, but we did have a value in this data set of 12. And so if you put your fences, right, here's 42.5, and you put them on a number line, and then you've got 12 out here, it lied outside of that fence. So that 12 is an outlier. In this data. You can have no outliers, one outlier, two outliers. I don't really see more than two happen very often, or it really wasn't very good data. Okay, last section in Chapter 3 is 3.5. 3.5 says we're going to compute the 5-number summary and interpret box plot. The 5-number summary, it consists of your min, Q1, your median, which is also Q2, Q3, and your max. So that's your 5-number summary. So example 1 says obtaining the 5-number summary. Every 6 months, the United States Federal Reserve Board conducts a survey of credit card plans in the U.S. The following data are the interest rates charged by the 10 credit card users of randomly selected for July 2005. Determine the 5-number summary. Okay, so the first thing that you're going to want to do is put them in order. And also this number is 14.5. So go ahead and put them in order from smallest to largest. And I'm just going to give you this information. And you can verify that you did it correctly. I always do my min and max first because it's easy. My min is 6.5 and my max is 14.5, so that last one down there. My Q2, I had 10 users, so I had to average them together. I had to average 13.3 and 13.9 and divide them by 2, and I got 13.6. Then my Q1 was 12. And my Q3 was 14.4. And that is my 5-number summary right there. Last thing we're going to talk about is drawing a box plot, and there are some steps. First step is to find the 5-number summary. Then to find your fences. We talked about that. To find the fences, you have to also know what your IQR is. Then draw a number line large enough to include the max and min values. And you need to put Q1, Q2, and Q3. And that's basically what's going to create your box. Label the upper and lower fences. Draw a line from Q1 to the smallest value and Q3 to the largest value. Those are called the whiskers. And then any outliers you denote by using a little asterisk. Okay, so I'm going to try my best here with all of this. So, let's see. I'm going to probably have to do it right here, but that's okay. Let's do it right here. Still can't create a line. Okay, there we go. Let's see. So our max is 14.5 and our min is 6.5. So I'm probably going to count by ones. Okay, and I'm going to write all my information again really quick. My min was 6.5. My Q1 was, let me find it again. Q1 was 12. Q2, aka min, was 13.6. Q3 was 14.4. And max, was 14.5. Okay, and I'm gonna go ahead and tell you I already did the outliers, but I would check and make sure you know how to do it. Well, actually, let's just talk. I did the fences. So, my lower fence was 8.4, and my upper was 18. Okay, so the thing I look at first is my min and max. My max is 14, so I know my upper is going to be over here somewhere, wherever 18. Oops, I keep trying to change colors. Sorry. Oh, it would help if my pen was on. Let's do this. So that's 18. That's outside of my data. So the upper really isn't going to be, there's no values that lie outside of that, so I'm good. But the lower, my min is 6.5, so I'm definitely going to have something that lies outside of this lower. And so I look, and I'm going to kind of star all the numbers. So there's 6.5. It looks like 6.5 is the only outlier. So I've got an outlier at 6.5. And now I can do my box plot. So you make the box with your Q1, Q2, Q3. So I'm going to draw a little line. So wherever 12 is, here's 12, 13.6. and 14.4. And then I'm going to draw a little box with those, okay? And then this one's kind of hard, but you draw what's called the whisker from the end to wherever your min and max are. So I'm going to do the max first, is at 14.5. And it's kind of hard because there's not very much room there, and it looks like it's at 15, but bear with me. And then my min is 6.5. Oh, not a great line, but anyways. And then remember, you asterisk wherever the outliers exist, so an outlier exists at 6.5. And that's what your box plot looks like. We can find the shape of distributions using box plots as well. So if the box is mainly, to the left over here, then we can say it's skewed right. If it's in the middle, we can say it's symmetric. And if it's most of the data is to the right, then it's skewed left.